So cylindrical coordinates are actually kind of simple. They're really just polar coordinates with an extra variable thrown in. And that means we already know how to write a triple integral for them. Because the triple integral would just be the triple integral over the solid of r theta z, f of r theta z, and then it would go r dr d theta, because that's how polar works, and then you would throw in your extra variable. And this is if you're doing it with respect to z, of course. If you're not doing it with respect to z, then you'd have to do dy or dx, depending on where your extra variable was. So we'll just make a little note. Third variable is most often z, but not always. And I think we'll see an example of that at some point. All right, so we're going to use a triple integral to find the volume in the first octant only of the solid bounded by z equals x squared plus y squared and z equals 9. Okay, so this is actually z equals r squared. And that's a constant times an r squared, which if we go back a page, we know that's a circular paraboloid, right? Z equals c r squared. So that's what this is. So this is a paraboloid, circular one at that. Oh, I can't remember. It's paraboloid. There we go. So it's going to look like this. So paraboloid, so parabola, circle around the top. And where we're hitting is actually at the plane, z equals 9. That's a horizontal plane. So, right, you're hitting at z equals 9 coming across like this. So it's going to touch right there at that plane. Okay, so this is z equals r squared. Right up here is z equals 9. Lovely. All right, so now we're only going to look at the first octant, though. So we only want to be in the first octant. And we have to think about the region of integration. It's down here, right, that we have a region of integration. And it's only that piece of it. Okay, so this is the surface that's drawn up here. Surface, or the solid, if you want to think of it that way. So we need the region of integration down here. So we need to redraw just that piece. And it's a portion of a circle because this is a circular paraboloid, so of course it is. But we need to figure out what radius this is. Okay, so to do that, we know that this is where the paraboloid and the plane meet, right? And they meet at z equals r squared is z equals 9, so r squared equals 9, so that means r equals 3. Okay, so we know this is a circle, a section of a circle of radius 3. And just in case you want to look at it, here it is, right? So here's the paraboloid. I made it kind of rainbow colored. And there's the plane, that aqua bit coming across at 9. And so what's happening is that it casts a shadow down onto the xy axis that we're looking at. Now we only actually want the first octant, which is just 1/4 of that, but our xy plane, but we only want 1/4 of it. So there you have that. All right, now how to find the volume. Okay, volume is the triple integral over the solid of 1 dV. Okay, so that would be the triple integral of 1 r, and then we can kind of go in whatever order we want. So I'm going to go dz, dr, d theta. That's actually the most common way to draw this, or to write this. Okay, so let's look at our theta values. Theta is the easiest to figure out. Actually, I'm going to change it so they're all different colors. One second. There, just to try to help us establish. All right, theta is and r are actually really easy in this case because we have to think about the region of integration. If we have a spoke coming out from the pole, r would start at 0 and go to 3. So that's easy enough. Theta, well, we're only in the first octant. So we start over here at theta equals 0, and we end up over here at theta equals pi over 2. So we're going to go 0 and pi over 2. So then where's the difficulty? it's the z. So you have to think about a pillar would be stacked inside this three-dimensional object, right? So what's the bottom and what's the top, right? So down here is the bottom, up here is the top, right? It'd be hitting that paraboloid down here. So the bottom is r squared and the top would be 9. All right, well, we can use our trick. So we can get rid of the theta. Now you can't do it with the r's, right, because that's not going to work, but we can do it with the thetas. And we can say, look, there's no theta anywhere in here, right? If you look, no theta here, no theta in anywhere of this, right? There's no theta, so we can use the trick and just make it become pi over 2 in front. Then we have an integral from 0 to 3, which we haven't done. And then I can integrate this with respect to z. That would just be rz. And I'm going to take z from r squared to 9. And then I still have dr to deal with. I can't get rid of the r because there's r squared in there. Okay, so then this would be 9 minus r squared in front. So this is pi over 2 times, and then this would be the integral from 0 to 3. And this would be 9r take away, I'm actually going to distribute this, 9r take away r times r squared is r cubed dr. And this particular one is so easy. I mean, we can do this by hand. This is not hard. So this is pi over 2 still in front times, and then this would become 9 halves r squared minus 1/4 r to the 4th from 0 to 3. The 0 is going to make nothing, right? Because these are polynomials, so no biggie. The 3 will become 81 over 2 minus 81 over 4, so that's 81 over 4. So the whole thing becomes 81 pi divided by 8. Oh, and we didn't get units, so let's pretend x, y, z are in inches. Just pretend that at the start. Then this would be inches cubed because this is a volume that we found here. Just to kind of throw in a unit there. And so you can see it in Maple. Of course I did it in Maple. And it's right here. Oops, I made that font too small. All right, so I have the original, so r. So I'm showing that that's that value, which is 81 pi over 8, and then I can see the numeric value. And then I put in my last integral, and that proves that my work to get there was okay, because the original integral and then my newly made integral all work out to be the same. They work out to be 81 pi over 8. So I know that I did it right. Let's do another one. Let's find the mass of the solid above the xy plane but below the cone, z equals 4 minus x squared plus y squared. Okay, so let's think about what that looks like for just a second. This would be z equals 4 minus the square root of r squared, which is 4 minus r. So z equals 4 minus r, but I want to be inside the cylinder, so below the cone, but inside the cylinder, this is r squared equals 4, which we all know is r equals 2. So let's look at that. Of course, I graphed it in Maple. So I graphed it a couple ways so you can see it. So I have the surface, I graphed it in regular plot 3D, and then I have it right there. You can see it makes this little house, which I like. And then I changed the coordinates on this one to be circular or cylindrical so you could see it. So, oh, except I messed with that. 1 second. There, I had to rerun my sheet. It wasn't happy with my graphing here. So I did this one with plot 3D, but I changed my coordinates to be cylindrical, and I just said 2, and it just made a cylinder, right? Which is easier in many ways than doing this whole implicit plot thing. That's the cylinder on this one, is this whole thing. But down here, when I establish my coordinates to be cylindrical, then it works. right? So it's whichever way you want to do it, but it looks like a house. It looks like a hut because you're below the cone, but you're inside that cylinder. Oops, and we can see the answer right there. All right, so let's look at the integral. We want to find, oh, and actually let's draw it. So we know that we have a cylinder like that, and then we have a cone on its head. There we go. Not the best drawn cone, but there you have it. Okay, so we have the cone on top. All right, so that cone up here is the z equals 4 minus r, and the cylinder is the r equals 2. So let me just kind of segment this off so you know that's something different. Okay, so this is 4 minus r, and then that is r equals 2. There, I rewrote it so it's a little clearer. Okay, now what about the region of integration? It doesn't say we're only in the first octant, so this whole bit on the bottom, that's our zone. So let me draw it. So this is the surface here. And we need both drawings because they help us with different things. So the surface is for the z part, and the region of integration is for the r and the theta part. So the region of integration is a circle. Now it's a circle of radius what is the question? Well, it's not much of a question because r is equal to 2, right? That's a cylinder. So we know this is r equals 2. Right? Okay, so great. So our region of integration, no problem. Okay, so let's establish. Mass is the triple integral over the solid of the density function of r, well, it's x, y, z dv. Okay, so we are going to have to convert everything into cylindrical coordinates. Our density was 5 minus z. Well, luckily for us, that's still cylindrical, so we're fine with that. 5 minus z is great. Then we're going to say r, right? Don't forget the r bit. Then dz, dr, d theta. Oh, and I'm going to do those in different colors to keep things clear. So let me do dz, dr, d theta. Theta is super easy. Theta starts here and ends here, right? Theta equals 0 and 2 pi. So 0, 2 pi, no problem. And yes, we are going to be able to use our trick and make it go away after a step, which we'll get there. All right, so then r, so you think about a spoke. This whole circle is solid. So we're starting at 0 and we're ending at 2. So that's easy. Constant and constant. All right, so what about the z? So you have to imagine a pillar stacked inside here, this hut, right? Trying to stack up a whole bunch of pillars inside the hut to find it. So the bottom would be z equals 0. And the top would be, where it's hitting that roof, would be z equals 4 minus r. That's the top, that's the bottom. So that's what we're going to do. We're going to put 0 and 4 minus r. So you draw both pictures because they're both useful, right? The three-dimensional one helps you with your z, and then the 2D region helps you with these two, the theta and the r. Okay, again, we're going to use our trick. I'm going to stop writing notes about it because we know it. So oh, that z is driving me nuts. Hold on one second. Let me change it. dz. There we go. All right, so we're going to write 2 pi out in front. And then we're going to say, we're going to do 2 steps at once because we're clever like that. So we're going to make this and this go away. So that's how we do that. We write the 2 pi right there. Now, I can't get rid of the z or the r because I have both of them sitting in here. So no dice there. And I have to do z first because there's an r right in here in the integrand. So I have to go in the order, dz, dr, d theta, which is the most common order. Okay, so dz. So if I integrate this with respect to z, it's 5z minus 1/2 z squared, and then I just have an r sitting in front of the whole thing. So I'm going to go from 0 to 2 for dr. And then it's going to be r times 5z minus 1/2 z squared. And z goes from 0 to 4 minus r. All right, and then I have a dr still sitting there because I haven't done it, so it has to be there. Okay, so that's 2 pi and then integral from 0 to 2. And then this would be r times, and then 5 times 4 minus r, minus 1/2 times 4 minus r squared. And that's it, right? Because the 0 would make everything turn into 0, so we're not worried about it. And we're going to make Maple do that, right? We're not doing that. No, 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 no. Right? So Maple, help, please and thank you. Right? So let's go grab Maple. All right, it's 116 pi over 3. Let's see what I did. So I have the original integral right here, and then the original integral numerically, and then I have that new one that I came up with at the end, and then I did it numerically as well. So that way I know that I did my work right, because by checking the original integral with my new integral, then I know that I have it right. Now, the one thing I will say is that I should have given us units on this, and I didn't. So let's pretend. Let's pretend this was in kg/meters cubed, just for the fun of it, right? So if that's kg meters cubed, then this is kg, right? Kilograms, because it's a mass at the end, and mass is measured in grams, kilograms, all that kind of stuff.